Google loads in 150 milliseconds. That's faster than a human blink. But between your keyboard and that search box, your request makes 6 invisible stops, any one of which can silently destroy performance. Think of it like ordering at a restaurant. You place one order, but it travels through a host, a kitchen, a runner, and a delivery chain. Miss any step, the whole table waits. This isn't academic. Google's own research. 100 milliseconds of extra latency reduces conversions by 7%. Amazon calculated that 100 milliseconds cost them 1% of revenue. At Amazon's scale, that's hundreds of millions of dollars per year, from a tenth of a second. The restaurant analogy holds. A slow kitchen loses tables. A slow web stack loses customers. Before any network call happens, Chrome makes a surprisingly smart decision. You type google.com, no protocol, no path. Chrome checks, is this a search query or a host name? No dots usually means a search, but google.com has a dot and a valid TLD, so Chrome flags it as a host name. Then it checks one more thing, and this is where the first optimization hides. Chrome ships with a hard-coded list of domains that must always use HTTPS, called the HSTS Preload list. Google.com is on it, so Chrome skips the HTTP attempt entirely. No redirect round trip, 0 milliseconds wasted. Most apps don't make this list. They waste 50 milliseconds on a redirect before the real work starts. Back to the restaurant. Google.com already knows your table number before you walk in. Now Chrome needs an IP address. This is like asking the host stand for the kitchen's location. Chrome checks its own DNS cache first, often a hit for popular domains. Cache miss? Ask the OS. OS checks etc hosts, then its own cache. Still nothing? Ask your DNS resolver. 8.8.8.1111 or your ISP. For Google.com, it's almost always cached at the resolver. Cached 1 milliseconds. Cold walk 200 milliseconds. Here's what nobody tells you. Netflix traced a 500 millisecond latency regression to a missing OCSP staple on their TLS certificate. OCSP is the mechanism browsers use to verify a certificate isn't revoked. Without the staple, every browser had to make a separate network call to a certificate authority before loading the page, adding 300-500 millisecond to every single user session. A certificate configuration issue hit millions of users. The fix was one line in an Nginx config. Chrome now has the IP, say 142.25.8046. It knocks on port 443. This is the TCP three-way handshake. SYN, SYN-ACK, ACK. Your restaurant analogy. You ring the doorbell, they say come in, you walk through. Costs 1 round trip. Same city, 10 millisecond. Cross-continent, 50 millisecond. Transoceanic, 200. Google's anycast routing means your packet hits the nearest Google POP, usually under 20 milliseconds for most users. Before any real data flows, both sides negotiate encryption. TLS 1.3, what Google enforces, completes in 1 round trip. The browser sends its crypto preferences. The server replies with its certificate and a session key derived via ECDH math. Both sides independently compute the same encryption key. No key was ever sent over the wire. It's like agreeing on a secret code by shouting math in public, and somehow only you two understand it. Here's where returning users get VIP treatment. If you've visited Google before, your browser holds a TLS session ticket, a cryptographic token the server issued last time. On your next visit, you send your GET request bundled with the very first TLS message. 0 handshake latency. The restaurant equivalent. The regular customer walks in, the waiter already has their usual order ready before they sit down. Old HTTP 1.1 had a rule, 1 request at a time per connection, like a waiter who can only carry 1 plate per trip. HTTP 2 breaks that rule. Multiplexing lets the browser send dozens of requests, HTML, CSS, fonts, images, over 1 single connection simultaneously. No waiting in line. Google's homepage fires off parallel fetches the moment the HTML starts streaming. That's why it feels instant. Over the encrypted tunnel, Chrome sends a terse GET request. It tells the server, I speak Brotli compression, I'm in NUS, here are my cookies, and I might already have this page cached. Here's my e-tag. That last part is crucial. If the page hasn't changed, Google returns a tiny 304 not modified instead of resending 14 Ks of HTML. The kitchen sends a ticket saying same as last time instead of cooking from scratch. Google's server responds with HTML compressed using Brotli, Google's own compression algorithm, open sourced in 2015. Brotli achieves 3 to 5 times better compression than plain text. Google's homepage HTML is about 14 kilobytes compressed. Uncompressed, it would be 60 kilobytes. Over a mobile network, that difference is a full second of load time. Better compression means faster first byte and less bandwidth cost for both sides. Your request doesn't go to one server. Google routes it via anycast BGP to the nearest of roughly 35 major data centers worldwide. The Google frontend, GFE, handles TLS termination and HTTP2 at the edge. From there, your request fans out internally to hundreds of search index servers in parallel. Results are merged and ranked in about 50 milliseconds. The kitchen has 35 locations and 500 cooks working simultaneously on your order. Google doesn't wait until the entire HTML is assembled before sending it. Chunked transfer encoding streams HTML bytes the moment they're ready. The browser starts parsing and building the DOM while the server is still generating the rest of the page. It's like the kitchen sending your appetizer while the main course is still cooking, rather than making you wait at the pass for everything at once. Now the browser takes over. HTML bytes become a DOM tree. Discovered CSS becomes a CSS-OM tree. Combined, they form the render tree, only visible elements. Then layout, compute every element's exact pixel position. Then paint, rasterize to bitmaps on the GPU. Then composite, merge layers and send to your display. This pipeline has 5 stages. Blocking at any stage freezes your screen. Render blocking resources are the worst offender. CSS is render blocking by default. If Chrome finds a style sheet link in the HTML, it stops building the render tree until that CSS downloads and parses. JavaScript is even worse. It pauses HTML parsing entirely by default. This is why Google inlines its critical CSS directly into the HTML. No extra network round trip for the styles needed to paint the first screen. The appetizer arrives already on the plate. While the main HTML parser is blocked by a render blocking resource, Chrome secretly runs a second lighter parser, the Preload scanner. It races ahead through the raw HTML, finds IMG, link, and script tags, and fires off those network requests immediately. It can't build the DOM, but it can start fetching resources. This background chef reads the recipe while the head chef is busy. Result: resources arrive before they're needed. Google created Core Web Vitals, a public scoring system for exactly this pipeline. FCP, first contentful paint, first visible pixel. LCP, largest contentful paint, main content visible. IM, interaction to next paint, how fast clicks respond. Google's own homepage hits LCP under 150 millisecond for warm returning users. The threshold for good is 2.5 seconds. Google is 16x faster than their own passing grade. Most websites aren't Google. They use a CDN, Cloudflare, Akamai, Fastly, to fake Google's global presence. When you type github.com, Cloudflare's DNS returns the IP of the nearest Cloudflare POP, maybe 35 milliseconds away. Without Cloudflare, your TLS handshake might travel 150 milliseconds to GitHub's origin in San Francisco. The CDN terminates TLS at the edge and keeps a warm connection to origin. Your restaurant opens a local branch instead of flying you to headquarters. Chrome doesn't just react, it predicts. When it renders a page full of links, it silently resolves the DNS for those linked domains in the background. It even pre-opens TCP connections to pages it thinks you'll click next. By the time you click, the connection is already established. Chrome's network stack runs in a completely separate process from rendering, so network I/O never stalls your UI. The restaurant's kitchen is already prepping the next course before you finish the first. Google didn't stop at HTTP2. They built QUIC, a transport protocol that runs on UDP instead of TCP. TCP has one fatal flaw. If one packet drops, every stream stalls waiting for it, called head-of-line blocking. QUIC fixes this. Each stream is independent, so one dropped packet only delays that one stream. Google properties serve HTTP3 over QUIC to supported clients today. It's like switching from one delivery truck to 20 independent motorbikes. Let's put numbers to every step for a new device. No caches, 50 millisecond round-trip time. DNS walk, 100 millisecond. TCP handshake, 50 milliseconds. TLS 1.3 handshake, first HTTP request, 50 milliseconds. Server processing, 50 milliseconds. First byte received, 300 milliseconds total. CSS and JS fetches, 50 milliseconds parallel. First contentful paint, around 400 milliseconds. For a warm returning user on the same connection, FCP under 100 milliseconds. Every optimization in this video moves one of those numbers. You can instrument every phase of this pipeline with Python socket and SSL libraries. Set a timer before DNS resolution. That's your DNS cost. Start the TCP connect timer after getAddrInfo returns. Wrap the TLS handshake separately. Time the HTTP get to first byte separately. Run this against google.com versus your own app. I promise you'll be surprised which step is your actual bottleneck. Most engineers blame the server. The data usually disagrees. Senior engineers know this distribution. DNS issues cause roughly 5% of latency problems. TCP and TLS together cause about 20%. Server processing, 25%. But client-side rendering, JavaScript execution, layout, paint, that's often 50% of perceived load time. Optimizing only your server misses the majority of the problem. When someone says the site is slow, the real question is, which course in the meal was late? In your next system design interview, say exactly this. Typing a URL triggers 6 phases. Browser parsing with HSTS check, recursive DNS resolution, TCP three-way handshake, TLS 1.3 negotiation, HTTP 2 GET with conditional caching, and browser rendering through DOM, CSS OM layout, and paint. Optimizations exist at every layer. HSTS saves a redirect, 0RTT saves a handshake, Brotli saves bandwidth, HTTP 2 multiplexing saves round trips. That answer alone separates junior from senior. This breaks everything you think you know about web performance. Most engineers think adding more servers is the answer, but a 2022 study of production web apps found that for 68% of slow page complaints, the server latency was under 50 millisecond. The bottleneck was always client-side JavaScript. More servers, same slow JavaScript. You can scale the kitchen infinitely. If the waiter drops every plate, it doesn't matter. Remember the restaurant analogy? Let's map every optimization back to it. You're a regular, host skips the greeting, takes you straight to your table. DNS caching, kitchen already knows the address. 0RTT TLS, your usual order is pre-prepared. HTTP 2 multiplexing, every dish arrives in parallel. Brotli compression, smaller plates, faster delivery. Preload scanner, kitchen preps sides while your main course cooks. Same restaurant, 16 times faster. Amazon, Google, Meta, they all ask this question. Not because they want you to recite steps, because the answer reveals your mental model of the full stack. Can you identify which layer is failing? Can you reason about where a latency regression lives? Can you design a system that optimizes all 6 phases, not just the one you're most comfortable with? The restaurant metaphor works here too. A great chef understands the entire dining experience, not just the kitchen. HSTS saves 50 milliseconds per cold visit. DNS prefetch saves 100 to 200 milliseconds. TLS 0RTT saves 50 milliseconds. HTTP 2 multiplexing eliminates 3 to 5 extra round trips for assets. Brotli cuts payload by 70%. Chunked transfer gives the browser 200 millisecond head start on parsing. Stack all of these. A 400 millisecond cold start page becomes 150 milliseconds for warm returning users. Every layer compound. You can't skip the chain, but you can optimize every link in it. Typing google.com is ordering at the world's most optimized restaurant. 6 courses, HSTS, DNS, TCP, TLS, HTTP, render. Google spent decades speeding up every single one. In your next interview, walk through all 6. Most candidates describe 3. That gap is exactly what gets you the offer. Subscribe. New system design breakdowns every day.